Section 10.3, curve sketching. So, here's the deal. In reality, we're supposed to use calculus concepts to come up with any vertical or horizontal asymptotes that exist. And we should also be using intervals of increasing or decreasing, and relative extrema points, and intervals of concavity, and inflection points, and y-intercept, and x-intercepts, and all that fun stuff to come up with a graph of a given curve. With that being said, I am going to be very easy on you and teach it algebraically versus from a calculus perspective, okay? In other words, this will basically be a review. All right, I'm trying to take it easy on you on one section, okay? Curve sketching. You're not going to have to curve. You're not going to have to curve. Ugh. You're not going to have to sketch the graph. I'm not going to make you do that, okay? All you're going to have to do is come up with any vertical and or horizontal asymptotes that exist. So, how do we come up with a vertical asymptote? Well, if you have a factor occurring in the denominator that does not repeat on top, and you can let that factor be equal to 0 and solve for x, whatever the x value is, that's going to be your vertical asymptote. I'll explain by way of example. Horizontal asymptote. Really, this is based on limits at infinity. Okay, limits at infinity or negative infinity. But, again, I'm explaining this algebraically. So here's all you got to know, these three things. Okay? If the degree of the top is less than the degree of the bottom, you have a horizontal asymptote at y equals 0. If the degrees are the same, it's going to be the leading coefficient of the top divided by the leading coefficient of the bottom. Y equals that ratio. That's your horizontal asymptote. If the degree of the top is greater than the degree of the denominator, then you do not have a horizontal asymptote. Let's look at some examples. As soon as I find them, we'll look at some examples. Okay, number one, find the horizontal and vertical asymptotes of the graph of the given function. All right, first off, vertical asymptotes. So, do we have a factor in the denominator that does not repeat on top? Yes. You let that factor be equal to 0 and solve for x. So, x equals negative 3 is a vertical asymptote. That's it. Horizontal asymptotes, okay? By the way, what's a vertical asymptote? It's a vertical line that the curve will approach but never touch it, never cross it. A horizontal line asymptote is based on a horizontal line, and it's really dealing with end behavior. What's the curve doing as you go to negative infinity versus positive infinity? Okay, I guess this is negative infinity, and this is positive infinity, my wrist. Okay, how do we do it? You look at the degree of the top, and you look at the degree of the bottom for determining horizontal asymptotes. The degree of the top here is 1. The degree of the bottom is also 1. Therefore, you do have a horizontal asymptote. Equal degrees. It'll be y equals the leading coefficient of the top, 2, divided by the leading coefficient of the bottom, understood 1. So y equals 2. All right, y equals 2 is the horizontal asymptote. Number 2, same directions. Determine any horizontal and or vertical asymptotes. Okay, so let's do the same thing. Let's vertical first. All right. Do we have any factors in the denominator? Yes. Do they repeat on top? No. So you let this factor be equal to 0 and you solve for x, and you get your vertical asymptote at 3. Okay, it cannot ever cross this vertical line. All right, it's undefined right there at that vertical line, x equals 3. Horizontal asymptote. Well, I have 1 plus this. That's interesting. Maybe I should rewrite it. Maybe I should rewrite this. So what's the common denominator here? Let's rewrite this function. The common denominator would be x minus 3, okay? So if that's the common denominator, then what do I have to change 1 to? Well, 1 would be the same as x minus 3 over x minus 3, right? So there's my common denominator already in place. So I'm going to change 1, just this 1, to x minus 3 over x minus 3. When you reduce this, you get this 1. Then I'm going to put a plus, and then I'm going to put a 2. Plus 2 over x minus 3. There it is. This means exactly the same thing as what was given to us. So now I could rewrite our function as what? As x minus 1 over x minus 3. Okay. It's easier, of course, now to look at this based on how I'm explaining how to determine horizontal asymptotes. Is the degree the same on the top and on the bottom? Yes. They're both 1. What's the leading coefficient of the top? 1. Leading coefficient of the bottom? 1. Therefore, horizontal asymptote? Yes. At y equals 0? No. It'd be y equals 0 if what were true? If the degree of the top were less than the degree of the bottom. Okay? No, this isn't right. What is the answer? Yes, very good. Y equals 1 over 1 or 1. This is correct. Let's look at our last example in section 10.3. Okay, in this scenario, well, a couple things going on. Let's look at each of them. So vertical asymptote first. Do that first. In order to figure these out, if any vertical asymptotes exist, I would rewrite this in factored form, okay? Be careful. So you get this over all of this. This is a little more interesting one here. So we get what? X squared. Let's completely factor this thing. And let's see what happens. Okay, so in this particular example, it's a little more challenging. And here's why. To determine vertical asymptotes, what has to be true? Well, a factor must only exist in the denominator and not repeat in the numerator. Okay? So let's see if that is the case in this particular one. And again, you have to factor it in order to come up with that. So do we have an x down here? Yes, we have an x in the denominator. Do we also have an x on top? Yes, we do. Doesn't matter if it's squared, cubed to the fifth, or whatever. We have this factor x repeating. Therefore, it will not generate a vertical asymptote. This one in the denominator. Look at the denominator first for vertical asymptotes. Look at the denominator first. You have an x minus 1. Does this factor repeat on top? It sure does. Because this factor is repeating on the top, it will not produce a vertical asymptote. Instead, both of these would actually create a hole in the graph of the function, but I'm not going to make you worry about that. Okay, moving to the final factor that occurs in the denominator, x plus 2. Does x plus 2 occur on top? No, it does not. So the only thing you got to worry about is this x plus 2. You're going to set this factor, which does not repeat on top, equal to 0, and you're going to solve for x. So the only vertical asymptote that exists on the graph of this function is x equals negative 2. All right, now, what about horizontal asymptotes? Well, I go back to the original one here, and actually, in the denominator, do you see, if you were to multiply these three factors together, that your leading term would be what? X times x times x, or x cubed. I'm saying that because it's important to understand that the degree of this denominator is 3, because the leading term is x cubed. So you have a 4th degree expression on the top, a 3rd degree expression on the bottom. Therefore, the degree of the top is greater than the degree of the bottom. Therefore, you do not have any horizontal asymptotes. D and E, they do not exist. Hope you're staying safe. Until next time. See you later.